Okay, I apologize for that. Good morning, everyone. My name is Stefan Romanowski, and I'm a professor of civil engineering at the University of Texas at Arlington. And today I will present you our work for developing a framework for estimating the damage caused by natural disasters on road and street network. And the framework includes the development of evolution models for each road section in a network, for two pavement performance indicators, the Pavement Condition Index, PCI, and the International Roughness Index, the IRI, using performance data recorded on each section before the flooding. And then the damage caused by the flooding directly through the increase in moisture in the foundation layers, or indirectly due to the increase in heavy traffic during the relief effort, is estimated by comparing the measured and the predicted condition indicator for each road section. And this methodology estimates the increase in pavement rehabilitation cost to the road agency, the increase in fuel consumption and gas emission for each road for street section and for the entire network. I would like to acknowledge my co-authors.
Excuse me, Stefan. Stefan, it's a little bit hard to listen to you right now. Can you get closer to the microphone, maybe?
Yes. Can you hear me better now?
Yes, that's better.
Okay. I really don't know what is going on, but anyway, I want to acknowledge my co-authors, Mohsen Taleb-Sava, Ana Maria Coca, and Constantin Popescu. They are doctoral students here at the University of Texas at Arlington. So the general concept is that a major weather event may affect the condition of some streets or road segments or some pavement structures. And if we can identify this, we can determine which streets or road segments have been affected. We can determine which design features make the pavement structures more resilient. And also we can evaluate the impact of weather events on the road street networks in terms of costs added to the users, but at the same time to the agency, the increase in maintenance and rehabilitation costs. So the objective was to develop a methodology to evaluate the damage caused by the hurricane flooding by comparing the condition of the pavement structures before and after the hurricane. When we started this work, we looked at the literature and we decided to come up with a new approach to the problem. We saw that some other researchers have tried to do a statistical analysis, and they try to compare roads that have been flooded with the roads that have not been flooded. But we think that that is misleading. We saw in one analysis, for example, that the flooded roads had actually a lower increase in roughness of the pavement of the IRI compared to roads that have not been flooded. So clearly something is not right there. We also saw that many studies have used FWD testing data. We also think that's misleading, and actually one of the reports mentioned that if the testing is done very early after the flooding, you will record a very soft foundation. Obviously the soil has been flooded, and if you extrapolate that, you come up with a very significant reduction in the life of that pavement. But in reality, the foundation dries out in time. So the timing of your FWD testing will affect your results. Our approach considers the fact that each road section is unique. And this is true because even though you might have road sections or street sections with the same configuration of pavement layers, they have been built in different years. They have received different rehabilitation work and repair work in the past. The quality of the construction maybe was not the same. So we decided to treat each road section as being unique. Our methodology or framework consists of three parts. First is you need to identify the flooded streets, the duration and the extent each street was flooded. I will talk more about this, that what I believe that our methodology is more suitable for street networks than for road networks. Then in the second part, from past condition or distress data, we develop condition distress evolution models and use these models to predict the condition at the time when the new condition survey was performed after the major natural disaster, and the reduction of time to the next rehabilitation action. And in the last part is to use this difference between measured and predicted stresses to identify the road and street segments that have been affected by the natural event, and to evaluate the financial impact, the increase in fuel consumption, in the CO2 emission. So in the first part, you have to identify the flooded streets, the duration and extent they were flooded. And in the paper, we show an example of the street network for the city of Houston. So here you use the street network and the flood raster files, you import them in GIS, and then the next step is to take the flood raster files in ArcGIS and convert it into polygon. And then what you do is you use the street network and the flood polygons to intersect to find the flooded streets. And this is a map that shows how we did it for the city of Houston for Hurricane Harvey. And then what you can do is you can identify in this way the streets that have been fully flooded. For example, a street here in the top right corner. This street has been fully flooded. And you can identify the streets that have been partially flooded. For example, the street to the west of that. Okay? So you can identify this quite easily. And we have obtained this flood maps for every day during Hurricane Harvey and a few days after. So for a total of 7 consecutive days. So to find the partially flooded streets, the flood raster files were reclassified into one class range raster, and then you intersect the flood raster files with the street grid, and you look at the attributes table for the flooded segments. And ArcGIS actually comes up with an attribute for the length of fully and partially flooded segment called the Schempp length. So, for example, here you have that obtained for this particular street, right? And then you take and obtain these attributes in a table, and you can calculate the percentage of the length of the street that has been flooded. Okay? So in our case, we assume if this ratio was less than 0.995, means the street was partially flooded. If the ratio was more than 0.995, we consider the street as fully flooded. So what you do is you get a table like this for every day, and then you use a VLOOKUP function in Excel, and you can assemble this into a single file. So for example, here you can see the streets that have been flooded in different days during Hurricane Harvey. And then you can combine the rows for with similar SectionID with using the Consolidate function in Excel to get store the data into a single table. And this way you can add up here and estimate the number of days that particular street has been flooded. Here you see how we can calculate the percent of length of each street that has been flooded. And again, you do this for every day during those 7 days. So for example, this first street was flooded 38% of its length in the first day. It has not been flooded after that. Okay. And then you match the flooded street with the partially flooded streets using the VLOOKUP function in Excel, and you can assemble all of this into a single data set. So now you have identified the streets that have been flooded for every day. So you have also the number of days each street has been flooded. So the second part of the methodology is to develop the distress models. And here you have to use historical distress data, and you get a better accuracy when you have data over several condition surveys. In other words, for one street, you have multiple values in time. And clearly in the data set, you can add other variables like the pavement age, like the truck percentage or the ADT, the truck volume. the time since the last rehabilitation, it's important clearly to look at the distress data collected only after the last rehabilitation performed on each street. You can include even the subgrade soil type or other variables that later on you can use in statistical analysis. And important is to have good distress survey data that has been validated, and again, they are collected only after the last rehabilitation work has been done. You assemble this into a table. This is quite common data that is stored by most pavement management system for cities and even state road networks. And then you can import this in Excel, and we have created an Excel macro that develops these nonlinear models. And we decided to use an Excel macro because it allows you to see what is happening when you run the analysis. You can easily test on a small data set. You can easily modify and adapt it to the format of the data that you have. Okay. So in addition, for example, to the section ID, to functional class, the surface type, the number of lanes, the length of the street, the traffic speed, the traffic volume, percent truck, and the measured IRIs and the measured PCIs, these are before the event, these are after the event. Okay. The other input values that you need to use is the discount rate and the growth rate for traffic, and the date of your analysis, the date when you are running the analysis, because it will calculate all the cost will be for the date when you run the analysis. So the first thing what the macro will do, will take for each street, in using the distress data points, will come up with a evolution model for that particular distress. In this case, for PCI, for example, we'll calculate this model. In the macro, we inserted a second order polynomial function, but that can be easily changed to any other function, any other distress model that the agency uses. And then it will predict the time when the pavement would reach the threshold level requiring the rehabilitation, the next rehabilitation level. If the event, the natural damaging event would have not happened, and uses the data collected after the natural event to estimate how much sooner actually the road will reach that threshold level, that the trigger value, the trigger level that requires a rehabilitation. Okay. So using this time, for example, you can find out that the effect of the hurricane is that for this particular street, you have a shortening of the time to the next rehabilitation of, let's say, a year and a half or 2 years. For the same thing, it will predict the IRI for the future. So we'll have a separate model that is used for the IRI. A major assumption here that is commonly used for distress models is that after the weather event, the deterioration trend is parallel to the trend that was before without the event. This is a very common assumption that is used. So the pavement deteriorates at the same rate, essentially. And then you can use this time shortening of time to the next rehabilitation, and you can use also the change in the PSI values, for example, to see if the road has been statistically, from statistical point of view, if the road has been affected by the natural event. So here, when you have a model, clearly you have a standard error for the model, and you can look at this difference. You calculate the ratio between the drop in the PSI and the standard error. And for example, if your threshold value that you decide is 2, for all the sections, for all the streets where this ratio is larger than 2, it means that from statistical standpoint, that street has been affected by the hurricane. And then you can use the data to identify features for those streets and see which features, for which features the streets have been more affected by the hurricane. You can look at functional class, the pavement configuration, for example, thick versus thin pavements, or asphalt surface pavements versus concrete surface pavements. You can look at the age, you can look at subgrade soil type, you can look at parts of your network different parts of your city and so on. And you can also see if duration of the flood has an effect on the condition of the pavement, again, from statistical standpoint. The next part is to quantify the impact of this extreme weather event. And here you have to look at the reduction in time to the first rehabilitation. So now, because of the extreme weather event, now you have to do the rehabilitation of the network earlier, of the streets earlier, or the roads earlier, because the condition of this pavements has deteriorated. So you have to use this difference in time between when the time to the rehabilitation, if the event would have not happened, and the time to the rehabilitation after considering the event has happened. So you have this difference in time, you have the number of lane miles for each road, you have the volume of different rehabilitation works, because you have to be you are at different level within your decision tree. I'll talk about that in a minute. And you can calculate this cost for the entire network by adding the cost for each particular segment, road or street segment. And then all the costs are discounted to the time in the analysis, because this cost would happen at different times, future times. So here you have to have a decision tree on what rehabilitation work is done. And you also have to have the cost per lane mile for each rehabilitation action. So this is an example where you have, for different functional classes, different surface types, the trigger values the values for the PCI that will trigger a rehabilitation. So for example, if you are between 60 and 45, the deterioration will continue. When it reaches 45, for this concrete pavement, you have to do a SAP replacement, and it will cost you $68,000 per lane mile. Okay. And this is very common. Most agencies have this decision trees, or what rehabilitation action they need to take, and also they have historical data, so they have the cost for each of this rehabilitation action. And the cost is estimated that will increase in the future, so you have that growth rate for the cost. So depending on when these are scheduled, the cost will be recalculated. Now, this would be the cost that happened to the agency, to managing agencies, but you also have a cost to the user. Why? Because if you look, for example, at the roughness or smoothness of the pavement expressed in IRI, you have a progression of an IRI before the natural event, but because of the natural event, the road becomes rougher. So when you have an increase in IRI, this has a significant impact on the vehicle operating cost. And the IRI is a major factor that affects the fuel consumption. So an increase in IRI would lead to an increase in fuel consumption. And an increase in fuel consumption, of course, leads to an increase in CO2 emission. So we have obtained this data from a national data set, and we have come up with, from their data, with a simple model that relates the increase in the fuel consumption per increase in IRI unit. And again, this depends if you have a car or a truck. We have assumed that all cars use gasoline and all trucks use diesel fuel. We came up with separate models for each. And this depends on the speed. So at different speeds, this increase in consumption due to increase in IRI would be different. So we came up with the simple models that can be applied, and the macro calculates that increase in IRI, predicts it for the future, and using these formulas will calculate the increase in fuel consumption. So then we have converted the increase in fuel consumption in increase in CO2 emission. And this again are some typical values that relate how much CO2 emission is due to burning of 1 gallon of gasoline, 1 gallon of diesel fuel. So essentially our macro, the way we built it, you have a series of input values description of each of the street in your network, including the traffic volume or percent of trucks. You could do this in more details if you have that information. You can have different classes for the trucks, for example, but you will need to have that relationship between the fuel consumption and the IRI for different classes of trucks. The measured IRIs and PCIs before the event, and measured IRIs and PCIs after the event. And the macro will calculate all this for you, will tell you for each street or road segment what is the next rehabilitation action that will need to be taken, when it will have to be taken. In this particular example, without the event, that rehabilitation action was to happen in 2027. Because of the event, now it has to happen 5 years earlier. We'll tell you if the hurricane, the natural event, had an impact on the performance, on the condition of that pavement. It says yes. What is the increase in rehabilitation cost, and what is the increase in CO2 emission? And it will calculate all this for each road or street segment, and all this can add it up to obtain the values for the entire network. So we developed this methodology that relies on the modeling of the evolution of pavement condition with time for each road segment, uses satellite fault maps and GIS maps of road network, and these are commonly available. And it helps identify the street segments affected by extreme weather events, and therefore the design features that reduce the impact. And it can also estimate the impact of the extreme weather events on the maintenance and rehabilitation of the road or street network, so to the managing agency, and the vehicle operating cost, increasing fuel consumption, and CO2 emission. I might say that there are some limitations to this approach that we propose. First of all, obviously, you have to have good historical distress and condition data. Without good data, you cannot develop those models for the evolution of PCI and the IRI. The methodology will not work if you have multiple events in a short period of time. So if you have, for example, a flooding every 2 years, you will not be able to build sufficient distress and condition data between the flood events to come up with reasonably good models. It is more suitable for streets network than for road networks. So this could be used more by city agencies, simply because, at least in Texas, for example, the state highways are built on a large embankment, and they are very rarely flooded, and they are less affected by flooding. During Hurricane Harvey, on straight highways, we notice more of erosion of the embankment than really flooding of the street. There are very, very few instances where the road has been flooded. And also this approach can be adopted to weather events other than hurricanes or floods. You can look at the effect of very severe winter that might, for example, might lead to significant low temperature cracking in asphalt pavements or concrete pavements. So you can use this approach to see if that severe winter has affected streets or road pavements, and how it has been affected. So this project will help cities and state agencies make more informed decisions about the pavement structural configuration, and it will allow a proper design of pavement structure, which will lead to a longer life of pavements for street and road network. So I will stop here, and I would like to see if you have any questions. I'll try to answer them.
Thank you very much for the excellent presentation, Stefan. So please, if anyone in the audience have any questions, we have about 5 minutes for asking the questions. Thank you.
And of course, more details are in the paper and in the final report for this project. This project was funded by Tran-SET in the year 2 cycle. So the final report is published.
Okay, any question from the audience? This is going to be the last opportunity. Okay. Thank you very much, Stefan. We're going to proceed now to the first presentation.